Good morning, everybody. Again, thank you for coming. Hopefully you will get something out of this worth your while. Usually we like to have these workshops fairly tight in scope because we would like you to get at least one or two things to take with you at the end of the day. So hopefully this is going to be the same thing. So now that we got our marching orders for the day, we can start the workshop. So today's workshop will be about topic is energy management, but as every one of you know, energy management can be a fairly wide topic covering everything. So we'll try to cover a couple of things that I consider important, especially for those of you who are new to energy management or who are trying to introduce energy management in your facility for the first time. So in general, when people talk about energy management, historically, what they were thinking is really, I'm managing the cost of the energy in the facility. That was what usually was thought about as energy management. I manage energy because I manage how much we pay for it. The problem, of course, with that is that now with the new regulations in place, GHG amount or your emissions coming out of the thermally fired equipment are the same regardless what cost you put it in at. So if you pay really cheap cost of commodity of natural gas, or if you pay a lot for it, the amount of emission is only related to how much you use, not how much it costs. So that's the general problem with thinking of energy management only on the cost basis. And we all know, we all face the new realities. Can we afford to do that going forward? Can we afford, with the cost of carbon impact, to be at the same mindset? Is there some business advantages to your business to being seen as green, to reduce the emissions, which means reducing the consumption, not just the cost of that consumption? And of course, some of your end customers may require a supply chain to minimize their energy intensity, which means that your process has to reduce energy intensity. Again, not a cost per se, but intensity as well. So how do we do that? We believe that energy efficiency is the best solution to reducing the energy intensity. It's the least cost option, and reducing the volumetric consumption of your energy will automatically reduce the cost. Efficiency can be gained. Usually people think about efficiencies as in, I'll buy new equipment that's much more efficient than the old one, which is fine. That can be done that way, but also upgrading your existing equipment or running your equipment smarter is also another way of doing the energy efficiency and getting the same impact for much less investment. And this is not just us. There's worldwide studies that confirm that energy efficiency is the least cost option to reduce your energy intensity and your energy usage, especially in the natural gas, thermal gas equipment. So how do we get there here? These natural gas energy efficiency programs have been offered by many, many utilities around the world. In Ontario, Enbridge Gas Distribution, our company, offers this program for over 20 years now. We started in 93, 94, way before it was cool to be green. And we call that demand-side management. So you on the electricity side, you hear about CDM. We call it the DSM, demand-side management. So over 20 years means that our team has accumulated enough experience to help you guys with advice, with ideas and financial incentives to get stuff done. These are some of our achievements. So we saved about 110 million cubic meters annually of natural gas to our customers, more than 20 million kilowatt hours of electricity, as I said, way before CDM programs were around, and over 800,000 cubic meters of water. So one thing to remember is that when we work with you on energy efficiency projects, we don't just focus in on the natural gas. There's always other streams of energy that are affected and that can be saved while we're saving natural gas as well. And this was only in 1 3-year period alone. So we've done much more over the course of 20 years. And this is only on the industrial side. We have similar programs for commercial buildings. We have similar programs for residential as well. So how do we do that? You have the brochures in your package, but our main program that we offer to customers such as yourself is industrial programs, and we call that custom industrial program, and we really mean it's custom. It means that these fellows in the white shirts, just like myself, go around, talk to the customers just like yourself on a daily basis, and we work with you to find a solution for your specific facility. So we will not have something that you can call us up and say, hey, what's the best makeup air unit for me? We just don't do that. What we do is we come out, we talk to you, we find, do you need a makeup air unit in the first place? Then we find the best solution how to supply that makeup, and then we get to the makeup air itself. So we help you with a holistic solution, not just with signing coupons for $50 at a time. And I can guarantee you that our approach will save you much more than just buying a new piece of equipment. The other program that we have deals with the energy management. We call it Comprehensive Energy Management Program. You have heard a lot of different energy management terms. This is much like strategic energy management. We called it Comprehensive Energy Management Program for a reason. We believe that energy management program needs to be introduced at a fairly slow pace to the facility, especially those that didn't participate before in energy management of any sort. And then it needs to be kept persistent. That's far more important than getting in there, spending $1 million on the equipment, getting everything measured, and then forgetting it in 6 months. If you go slow and steady, you will get persistent savings. And Comprehensive Energy Management Program will be tailored to your facility. So your facility will not go at the same pace as his facility, and therefore we will have two different approaches for the facilities based on what you really need. Again, just like our custom program, there is nothing that we come in with a specific set and we say, this is how you do it, and that's the only way you do it. We also like to cooperate between the electrical utilities and ourselves. So when we start energy management program, we like to have both utilities on board, if that's possible, only because it's very hard to institute a change in the mindset of people to conserve energy if you only tell them conserve one stream of energy, don't worry about the other one. That never ends well. So what is energy management? If I asked you what your opinion on energy management is, what would it be? First thing that people think of is standards and regulations. And everybody's heard of ISO 50001. Everybody's heard of superior energy performance. Those are the better known standards, but that's not the only way to save energy. So exactly like Senkan pointed out, it's any which way it works for you to save and manage how much energy you consume and at which cost, of course. For me, these are the two key elements of success. For any energy management, I don't care what kind it is, I don't care what you call it. If you don't make energy visible to the people on the floor, you will not succeed. Guaranteed. And you have to start treating energy as you treat other raw material inputs. You track. I come from industry. I spent many years working in industry, not in the energy. So I can tell you that we treated raw materials like gold. We knew everything what happened to that raw material. Once we bought it and it came into the facility, we knew where something goes, how much scrap it is, how much quality control problems we had, everything. None of us knew anything about energy. We didn't care. We spent, I believe it was about $1 million, 1.5 million cubic meters per month in natural gas where I used to work. We never cared where 1.5 million cubic meters of gas goes. It was just cost of doing business, and it was sort of like a fixed cost. And I'm here to tell you that it's not a fixed cost. And once you get that, once your facility accepts that there's variability, that's when you can start saving energy and costs. So why would you do it? There is all sorts of ancillary benefits to saving energy. It's not just about energy itself. One is better preventative maintenance. you increase your uptime, you enhance utilization rates if you can see that something's going wrong. If you see a trend that your oven for the painting keeps using more energy, that you need to increase your setup points over time, you can see that something's going wrong. And that will be seen also in your quality problems. So you can use energy management actually as an early indicator of the quality problems that you're going to see later on in the production. You can make operational improvements. If you know exactly what is the impact of changing set point by 5 degrees F, then you can go and talk to the operator and production manager and say, hey, changing this down by 5 degrees F will save 700 cubic meters a day, rather than saying it's a good thing to save. That really doesn't lead to action. If you can put the number, if you can put an actionable number behind something, they will be more likely to do it. And of course, to make better capital investment decisions. I cannot tell you how many times since I started in this role, I got to the facility and people want to install, I don't know, infrared heater in their facility. And they're convinced that's going to save them 30% of their energy. Yet their whole seasonal load in that facility is maybe 5% of their energy use. There's nothing they can save 30% in their infrared heaters. But they didn't know. They didn't know how much each piece of equipment is using. Energy management can be then used to say, where is my buck best spent today? So if good energy management conserves energy, reduces emissions, and saves money across the organization, what does the energy management structure look like? What do we need? So one is obvious, Senka pointed out, you need a means to control the energy consumption. And by that, I don't just mean control it. I actually mean how are you going to link what you talk about energy to how operator runs the equipment. It has to be embedded into every aspect of organization. We start with energy management teams, but those energy management teams need support of everybody in the organization. They cannot do it on their own. They will just not have enough time to catch up with everything. And they will not know every aspect and every reason why energy is used. So I look energy management more as managers more as a quarterbacks. They tell you which direction to go, but it's up to the people on the front lines to actually implement it. And they have to feel like that's their job. That they have to feel part of it. And all of that is because we want to make that energy visible. We ideally, in an idealized world where I want your facility to go is when you talk in the Monday morning meetings, you say how much scrap you made, how many days off you had. We should talk about how much energy did we use that week for the production. That should be part of the report that production looks at, not energy manager people, production people. Because that makes it real, that makes it impact. So our program takes a few steps. We need senior management sponsorship, because without senior management sponsorship, we cannot really proceed. We don't have that wide support. That it's not the same as if energy manager steps in front of the 100 people and say we're going to be green from now on, and when VP of production steps onto the floor and says we're going to be green from now on in. Followed by the energy team consolidation. We need to know who are the champions, who are the people who are interested in doing the energy, who are going to be enthusiastic about it, and who can actually rally the other groups around them. So energy team consolidation is a very important step. Long-term energy reduction goals. Now that you have support from the senior manager, you have the team in place, even if that's just one energy manager. But now you need direction. What are you going to do? What is this action going to accomplish? And this initiative, that long-term energy reduction goal, you can call it energy policy, you can call it reduction goal, you can call it whatever you want, as long as it's actionable item that you're going to follow when you do this. And then the last step is continuous improvement. And for those in the industry, they know everything about continuous improvement. We really want to get to that step because now it allows you to use energy management just like you would use quality control, just like you would use environmental issues. You go through the cycle of observing, identifying, executing, and verifying and acting on it. Once you're in that stage, your energy management becomes almost self-fulfilling. It's much easier to manage energy once you get to that stage. So let's see, why would we need this? As we said, senior management sponsorship conveys a message that organization is behind that. It's not somebody loner. It's not somebody who just believes in green and they're really interested and they're pushing for it. No, it's the organization that's pushing on. Energy team consolidation, they're the ones who will lay out the framework. They're the ones who will tell the organization which way to go. Why do we go there? What to investigate, what to drop off, how to put priority list of the energy management in place. And lastly, long-term energy reduction goals. Those goals will set up success for the later investment. Because once you start investing in it, you want to know that your dollars are well spent. Because there is nothing worse than starting a new initiative, spending few first dollars in the wrong place, and getting really bad ROI. That will kill that initiative for the next 5 years for the senior management. They want success. So we always advocate, even if need be, start small. Save $100, but save $100. Because if you promise to somebody you're going to save $50 and you save $100, it's much better start than if you promise somebody you're going to save them $50 and you save $0. And then we go into the continuous improvement we talked about. And that continuous improvement is nothing more than, if you think about it, it's just common sense, right? You want to ultimately, energy management is about savings. Savings in energy, savings in cost, savings in resources. But you want those savings, you cannot achieve them without some action. If you don't do something, if you don't change something, you will not get to the savings. So we want those actions to be based on the knowledge. We don't want them, the decisions that we make, we don't want them to be based on guesses. Today, a lot of decisions in energy management are based on guesses. We feel this big piece of equipment here, it must be using a lot of gas, let's invest everything there. But if that's only runs 1 day a week, maybe you don't use as much gas as you think there. Maybe that's a wrong investment. So we want this team, this energy management team, to base their decisions on knowledge. And how do you get to the knowledge? You collect information. So collecting information in energy management. This gets really interesting because whenever we talk to people to say, let's observe your energy use, the first thing they do is, oh, this is really expensive. It's going to take me all these meters, and it's going to be really expensive. We don't have money for it. And they give up. Well, I'm here to tell you that observing energy use is not about measuring everything. It's not step one. Because if you have a facility like this, how many meters do you need? And what do you tell your management? You know, at $3,000 a pop, I need 28 meters. What are you going to do with it? What are you going to promise your stakeholders the payback will be for that investment? So observing energy use really then leads to a lot of stress. And I don't know if you've heard the term analysis paralysis. We use it a lot in our facility. It's because people started overthinking it. And they said, ooh, this is now so complex, we cannot handle it, we just won't do anything. Because if I don't do anything, I can make a mistake, it's all good. The problem is you don't move then anywhere either. So what's the middle ground? How to get somebody to actually do something without scaring them into inaction? So that's why we have those ladies and gentlemen there in white shirts. They're there to help you. We've done this before, so we can help you break down the complex task into more manageable little steps that we can do one at a time. This is why our energy management program is called comprehensive, because we don't believe that we can just start and putting everybody on a $1 million energy management information system. That's not the right solution for everybody. So we can start with the smaller details. And one thing to remember is energy management is an enabler. I don't particularly like when people talk energy management will save me money, because it's factually not true. Energy management will not save you anything. Energy management will enable you to save money. It will enable you to spend money more wisely, but it will not actually do it. I have all sorts of computers. I have all sorts of equipment, and they pop up with all sorts of messages and say, you have a meeting in 5 minutes, but if I don't get up and go to the meeting in 5 minutes, computer will not go for me. The same thing happens with energy management. Computer can say, can flash red screen. You're using too much energy, you're using too much energy, you're using too much energy. If nobody actually does something about that, computer will not save energy by itself. So energy management, we cannot talk about as a savings. So when you hear energy management will save you 5%, no, energy management has a potential to show you how you can save 5%. It will not save you anything. So that's why we provide additional funding. We know that to get started into the energy management, you cannot really promise money to the management. So there is no payback. So that's why we offer money for the meters, so that you can start at least in the right direction. So observing energy use is not actually measurement itself. Measurement is the end, but it starts with energy use analysis. Where do I use energy? Where does my energy go in the first place? Where is it worth my while to put meter, where is it not? And all of that starts from the understanding your processes and the knowledge development about your process and your energy use. So really, when we talk about observing energy use, it starts observing my process, understanding my process, how does energy fit into that process, analyzing where everything goes, and then measurement. And that way, you will break down almost every measurement task into something manageable that you can both afford and that will get you somewhere. I can tell you from experience, we had not energy management, but we measured overall process efficiency. For those familiar with the term, that was very fashionable in early 2000s. Everybody wanted to know what their process efficiency is. We had the production lines, 5 of them. And on one production line, we installed $250,000 system that gave us 2,295 points of data every minute about that equipment. We calculated overall process efficiency. It came out to be 147%. Because we did not have time, nor did we have capability to actually calibrate all of those 2,295 points. So when we went into the second implementation, we actually started with 140 points. We calibrated each one first, and then we built off of that. Same with energy management. So how do we understand your energy consumption drivers? One way of doing it is you look at what is your source of data. Where do you get information how much energy you guys use? You can look at your bills. You can talk to one of our energy solutions consultants who has the data from our side for either, depending on your meter size and your meter setup, it can be hourly, it can be daily, it can be monthly. But we have the data if you don't have it. And then you convert that into some sort of visualization. I'm a visual person, so for me, charts work. But if spreadsheets work better for you, do spreadsheet, whatever it does. Whatever works for you, that's going to give you some idea how your energy is used. How do we identify then and prioritize improvements is a second step. Now that we know where energy is, what's the next step in implementing some sort of energy management system? Are we going to do the whole facility? Or are we going to do just a major energy user? So for me, if my goal is to do it at the least cost scenario, I would, based on the energy analysis, I would pick major energy user, and I would put sub-meter on that major energy user. I would learn my lessons on that one piece of equipment. You can keep it less resourceful, resource heavy. It's not as much investment, and it's going to teach you a few things what to look for. The other thing is, not all meters have to be real meters. We have people very often asking us for financing incentives for the makeup air units. I want to know how much energy goes into my makeup air unit. Well, makeup air unit is one of the easiest things to quantify energy on. If I know how much CFM that goes through your makeup air unit from fresh air, I can tell you how much that unit uses for every hour of the day. So why would you pay $3,000, $4,000 to install the meter if you can do that with a simple calculation? Better yet, you can put one of those amp meters on the unit, on the fan, so you know exactly how many CFMs you're pushing through, and back calculate what's the energy used in your gas consumption. So that's an example of how we do this without spending thousands of dollars on the meter. The other thing is people tend to put meters a lot on the pieces of equipment, they have no control over. In other words, if you put a meter to something because you want to manage the energy, managing the energy must imply you're willing to change something about that piece of equipment. And I can't tell you how many times people are like, I want to put a piece of equipment, I want to meter this piece of equipment. And when I ask them, what are you going to do with information? How are you going to change it? We can't change it. This is like a secret recipe. We cannot change anything on the piece of equipment. Then what's the point of metering it? What are you going to get? If you can get actionable item out of the meter, leave it for later on when you have everything else set up. Everybody is very concerned about collecting data. And that's a good thing. But when you have a lot of data, you have to make sure that the data actually makes sense. And one of the first steps, we need to make sure that the interval at which the data is being taken is always the same. One of my first energy management analysis that I've done for a customer, they had electricity data, gas data, and the water consumption data, all at the different intervals. So you couldn't actually ever find a correlation between all these energies because one was taken at 8 o'clock, one was taken at 8:05, the other one was taken at 8:10. So the chunks of information were not relatable one to another unless you did a very complex spreadsheet analysis and you put back everything into something that makes sense. So make sure that if you're collecting data on some sort of interval, that all the data you're collecting is on the same interval. It has to start at the same point, it has to end at the same point. And one thing that people always tend to forget is this is a shiny new toy, so they collect data on, I have a new computer, I can collect data every second. But I have production information for every week only. How are you going to correlate the two? What's the point of collecting your data for every second then? So if you're new to this, and if you have no other experience, I would always advise using the same interval for collecting energy data that you're doing for the production. Because that will buy you good graces from your production staff, because you will not change anything in the way they do it, and they will understand what you're talking about. So now we have what are we going to measure, where are we going to measure it, why are we going to measure it, and what interval time we'll measure it. Now, this is enough to start looking at the metering infrastructure. Now that you have that, that defines your scope of work. And once you have scope of work, this is the time when you give this over to somebody who is really experienced in meters. People are very afraid of analyzing their energy, but then they want to be involved and know exactly which meter they're going to spec out themselves. There's people who know that way better than we do. Rely on them. As long as you give them a proper definition of scope of work, you will get the right meter. So for you, it's far more important to focus on all of those things that we talked about rather than what type of meter you're going to get. Because if you put that in a scope of work, somebody will give you that proper meter that's going to measure what you want. Sometimes, for some of you, it'll be enough to have the data from your meter that's on site now, our Enbridge's meter. And some of you don't have access to that, but you can. And you can talk to your ESC about this methodology, but some of the meters can actually be tapped into. We have a specific contractor who does that, and he's the only one who can touch those meters. But you can actually tap into the meter and get that meter over information into your system. So you don't have to wait for any one of us to give you that information. You can put it into the spreadsheet. You can always have that at your fingertips. We offer incentives up to $1,000 towards that. Usually this exercise is between $1,500 and $2,000, depending on the complexity of it. So it's a very inexpensive way to get initial data into your system. And that doesn't work for everybody. That doesn't work for size of OEM manufacturer, for example, because they will have so many different points of energy use. But it will work for some of you. The other thing is, do not collect only energy data in your system. For whatever you're going to use to collect energy management data, must be able to accept the data from your production system as well. In other words, you have to capture what is driving the energy use. Because if you want to do any sort of analysis on energy consumption, you have to relate it back to the energy drivers. And we'll do more of that in the second half of the workshop. But keep that in mind. You have to keep track of it. You cannot rely on somebody's writing on a little post-it notes, we made 3 parts today. That's not going to last very long as your method of analysis. Goes back to the old saying, how do you manage something you don't measure? If you don't have information, you cannot manage it. This is part that's very important to me personally, because I think people don't understand that very well, is that if you track energy by itself, and lots of energy managers do that, they just go off onto the corner and they say, I'm going to track only energy and nothing else, you will miss the point of it. You will say, this is something that's off into the side. We cannot control it because there's only one person who knows how they control this energy. That's a wrong approach to the energy. Energy must be controllable. And the only way to do that is to actually accept that energy consumption is part of our decisions. When we make decision what equipment to buy, we are making decision how much energy we're going to use in the facility. When we make decision on how we run our equipment, we're making decision on how much energy is going to cost us. When we make decision on when do we go down for maintenance, we're making decision on energy usage. You will have many, many, many people who will run, for example, paint lines and those ovens on the paint lines with the small parts, and they will think that if they don't run parts through the oven, they don't use any energy. Where in actual fact, maybe 5% of their energy is actually going into the part themselves. So they're still using 95% of the energy, whether they actually operate on something through the oven or not, as long as that oven is on. And that's within the control of us who work down on the production floor, if we understand the consequences. So the last bit, you have to be able to set up a system. As part of the energy management system, there has to be a system where people are allowed to act. If they get information is confirmed, you have to allow them to act on it. Because if you don't do that, as we talked about before, if you don't have that taking action part, everything falls apart. There's nothing worse than giving somebody an idea that they can change something, and then when they have an idea and say, oh, I have an idea, let me change this, and you say, no, you can't change that. You will kill that initiative at the very start. And you will not get any more ideas, or ideas that you will get will be very checkbox-like, that you don't really want. And this is an example of one of those, why is it important to act, and why is it important to know what influences our energy use. Let's say the blue line represents the energy use over time. So here we have a spike in the energy use. Here we have a spike in energy use. And we look at that and say, is this okay? Is this something to be worried about? How do we know? And the only way to know is if you have some sort of baseline model. If you say, this is my expected consumption based on the drivers that I'm aware of. And then you say, oh, based on that, this is normal consumption spike. So I see a spike, but there is a reason for it. I don't have to worry about it. I don't have to alert anybody. I don't have to go run around. However, this one, we have no idea. Therefore, I'm going to act on that piece of information, not on the one prior to it. And you will not know that unless you have the baseline model. There is no way you will know that any other way. So how do you do this? How do you build the baseline? So this is where we're going to go into the break. And when we come back, we will start. I will give you USB sticks. And then we'll start looking at how to build the baseline model going forward. OK? So let's take a 10-minute break. All right. So let's continue on with our thing. I'm told that we'll increase the temperature in here a little bit, so you don't have to be afraid of freezing to death. It's not an energy efficiency measure. It's just wrong setting. So we were at the baseline, how to build a baseline. And the rest of this workshop will really focus on, let's look at building one simple baseline for a simple model. The simplicity of it can be extended to any complex project you might have. Don't be fooled by the simplicity of the sample itself. The principles are all the same. So as somebody smarter than me said, every journey starts with a single step. In energy management, it is best practice to start with building a baseline. Even before you purchase energy management system, even before you decide you want to do energy management, baseline building is one of the steps that I recommend as step one, because if nothing else, it will tell you what is the potential you see in energy management. And we'll get through that as we go through the example. So first thing, as we said, we have to define the boundary. Where are we going to put our energy management system? What are we building the baseline for? Are we doing it for the whole facility? It's best suited for the people who have very simple energy usage. They have one, maybe two users of energy, and they only have one, maybe two energy drivers. So weather and the production on a single line of single product, those are the people who can do whole facility management to start with. Major energy users, those are the people who have a little more complex energy drivers and or users. So if you have all these energy users everywhere, you don't necessarily have the pipelines as cleanly defined as this. Something goes off this pipeline, something goes off that pipeline. Once you get into that situation, it's best to focus on one energy user at a time and build the system based off of that, and then build them as together as in a grand system, if you will. It limits the scope, it limits the investment, and it, as I said earlier, it builds you knowledge and experience on how to do it elsewhere. So for us, we will monitor one line within the larger facility, so only one production line. Produces one widget every minute, operates 16 hours per day, 5 days per week, and it's in GTA area. So those things define what the other weather conditions are, and it define what our production driver is for this energy usage. Base period, as I said before, you can use pretty much any base period that suits your facility. So if you have only the process load that doesn't change, so you will always run the same product through the same process all the time. That accounts for 90%, even more, of your overall thermal load. Production drivers are steady, so you don't have January really low production, March really high production, then June again low production. If all of those are steady, you can use weeks, even months, to look at your energy usage and build the baseline on. Anything else, if you need full load seasonality impact, if most of your energy drivers are related to the seasonal outdoor weather, then you really need to look at yearly data for your consumption to capture the seasonality effect. However you slice it, base period must encompass the entire range of that energy driver's peaks. Otherwise, you will not build a proper baseline. So if you're building your baseline for summer months, for the seasonality of 1 year, you will get the wrong outputs. So you have to look at for the whole year if your consumption is affected by the seasonality. We already talked about this. One thing that I haven't mentioned before, if you have monthly data, and that monthly data can change, then don't only use 1 year data, use 2 or 3 years to smooth out all the potential changes. Otherwise, you will run into potential problem with 1 year being off year for whatever reason. And you will build model for that off year rather than for your typical conditions. So in this case, we have monthly consumption data available for the past 2 years. And our load is only slightly dependent on seasonal temperature, so we will use entire year as a base period as a test. So on your spreadsheet, at the very first tab, you will have this data as it is here. You will have a timestamp, so once a month, outdoor weather, typical weather in the GTA for that month in 2013. Production output, as I said, it's pretty steady because it's a 1 widget per cycle. And this is our assumed consumption of natural gas as measured in that 2013 year for that particular facility. So all of those data have been collected based on the inputs that we just talked about. It's simple as that. You can have this in hourly version, you can have it in daily version, you can have it in yearly version, however it is, the principle is always the same. You always first collect the data. What do you have available?
What would be the unit for your production?
This one is just widgets, number of widgets that we make. Yeah. So we make, for example, 21,000 widgets, 120 in January of 2013. And out of that, as I said, I'm a visual person, so I built the graph. So this is what it looks like. Blue is natural gas consumed. Yellow line is outdoor weather temperature, as on the right axis, and plotted for every month. And on the bottom in gray is the line that represents production output. So once I look at that, essentially, I'm analyzing what the graph is telling me to do. Is there any patterns in the data? There is a slight seasonality in the middle of the year, but not very pronounced. The production output is very steady. So that tells me nothing much changes from month to month production-wise, a little bit of seasonality impact. So that's what I can expect out of the model. So that's step one in almost checking what the model will tell you. If your model tells you that your seasonality affects it much more than what you see here, it's time to recheck your model. So something as simple as that will tell you what to expect in your output, so you know what it is. I used to do a lot of finite element analysis in my very first career, and I was always taught that if you don't know what finite element analysis is supposed to tell you, you will never know how to run finite element analysis. And that is very true, because doing finite element analysis, and at that time we let the computer run for like overnight, and come in the morning, you need to know what to expect. If you don't know what to expect, you wasted the whole day. Same here. You need to at least intuitively expect something. What will data tell you? One thing that I also do with data, in this particular case is not very indicative, but it's good for some sites, is I plot consumption versus outdoor temperature for all those months. And use, at some point in time, what you can actually get to is there will be like a drop-off. It'll go like this, and it'll drop off and line out, somewhere around 12 degrees Celsius. What that tells me when I look at the data is that your facility, once it reaches 12 degrees Celsius outside, does not use any more heating energy. And that's very important because lots of people will base their assumption that heating your facility to 20 degrees Celsius every day uses so much energy. Well, that's not true, because if you look at how your consumption works, in that case, it would be only heating it to 12 degrees Celsius. Once it reaches 12 degrees Celsius, you're not actually using heating energy. So your business case for replacing your heating equipment would be completely wrong to begin with, and therefore your return on investment would be wrong as well. That's why it's very important to know what the data is telling you. Next step, have we identified what drives the energy? So we looked at that other graph, and we assumed it's production because we use it in production process. There is a little bit of seasonality, so outdoor weather affects the energy use. What else affects it? And this is one of the things that people often fail, is because they don't want to involve production in their big, grandiose plans. They think they know everything, but production really knows what drives the energy. So if you think about it from the perspective of energy manager, the best friend you can have is a process engineering. Because you can go to them and you can say, hey, I see that production influences the energy. How do you use energy? What actually drives the energy? And they'll be able to tell you pretty closely. They will not know they're talking about energy, but they will tell you how the process actually runs. So some people call that energy mapping. Some people call it walking the process. There's many different names for it, but essentially you want to find out what influences the energy. Is it somebody on the floor who can tweak the setting? Is it computer that goes for a certain set point? What drives the energy use? So once we have that, we need a way to connect consumption to our drivers. Therefore, we need a model. And a mathematical model is a numerical expression. You can read this. But essentially, it connects all these inputs, weather, production, additional drivers, puts it into some sort of black box that we call a formula and a model, and it gives us predicted energy consumption. That's all it is. You can have, instead of weather, production, additional drivers, you can have 15 additional drivers. You can have a really complex system, but it always goes back to this model, to the same formula. You just keep adding the factors on the inside, on the input side. So essentially, we are answering the question, what is the relationship between the output and the input? What's the relationship between those variables? That's all the model is. As I said, as complex as it is or as simple as it is, this is the answer that it's going to give us. And to do that, we have one dependent variable. We call it y variable, and you can also think of it, what are we trying to predict variable? That goes on one side of the equation. On the other side, we have one or more numerical or categorical independent variables. Those are those x variables. For us, x variable will be production and the weather, because those are the things that we use to explain the predicted variable. So this particular regression model will have, all of you know the formula for the straight line. We have intercept, we call it A. This is the consumption where the explanatory variable is 0. So for example, if we have consumption of 200,000 cubic meters a month and we produce 0, your intercept A will be 200,000 cubic meters. And that means no matter what production you run, that's your base state. That's how much gas you need just to keep the lights on. And then you have B as a slope. And slope is the rate of change. So the more factor changes, faster it changes consumption, the B slope is going to be bigger. So the higher the slope, the faster the change. So if you go from 1,000 tons per a month of production to 2,000 tons of production per month, and you can increase your production by an equal amount, you get 45-degree slope. You can go more than that, you can go less than that. The lesser the slope, the less impact has the change in whatever you're doing to your consumption. And all of that to get to this formula. Predicted natural gas equals A, meaning that intercept, plus, in our case, it's going to be outdoor weather times slope 1, plus production output times slope 2. And you can go and add these slopes as many as you want. You can have B2, Bn, B15, however many you want. Formula never changes, though. So we have, on the USB sticks that you got, on the first tab, you have the input as it is. On the next tab, we have rearranged input a little bit to be able to get the regression model to work in Excel. There's nothing for you to do at the moment, but keep this in mind when you're doing energy model and any sort of statistics. Yes? Oh, sorry. Does anybody else have, is without USB stick? No? Okay. Sorry.
That's okay. Thank you.
Somebody said about statistics, there are 3 kinds of lies: lies, damn lies, and statistics. And this is true. People use statistics for all sorts of things. Usually they make up a story. They come up with a solution, and then they build a statistical model to justify the solution. And you can do that with everything, including the energy. So you have to keep open mind. You have to understand, are you doing statistics for the sake of doing statistics, or are you doing it to do energy management? And then you have to be honest with yourself and with your facility to say, yeah, this model doesn't or works because of these reasons. So that's all to say that no matter how complex model you have, and some of you will work with the models just like this one that we're going to do as an exercise here. Some of you will have very sophisticated models. If you will spend a lot of money in energy management information systems, none of them is a replacement for common sense. If the model tells you something intuitively that you disagree with, check the model. No, I don't care how complex it is. I don't care how many vendors are telling you this is absolutely true. Check the model. Correlation, R squared. Everybody's hung up on R squared. I have R squared of 99%. Good for you. 99% R squared, correlation here in 0.99. Between US spending on science, space, and technology and suicides by hanging, strangulation, and suffocation. Do you think those actually have cause and effect between them? But you have really good R squared. Cannot tell you how many times I've worked with customers who says, I have R squared of 98%, my energy model is perfect. Yeah, but it says that the higher the temperature outside, the more gas you use on your seasonal effect. Yeah, but it's accurate. No, it's not. So use common sense. Correlation does not always mean causation. It can be purely incidental. That's why you have to use common sense when you do statistics, just like you use common sense every day in your work. Check. If in your gut, if intuitively you disagree with the model, check it. Check it again. Ask somebody else to check it. Because this happens a lot. If you go to this tylerwigan.com, you can find all sorts of things like that. You will be amazed what people can correlate and cause. So now that we know, let's check, right? Who can check if the drivers that we assumed will drive our energy is actually driving our energy? Us. Only you. You who build the model are the only ones who can judge the model. You cannot leave it to the vendor. You cannot leave it to somebody who has never been in your facility, but he's expert in energy management. Because energy management in industrial facilities is drastically different than energy management in the commercial space. Drastically different. So you guys are experts in your facility. You're the experts in how to interpret the model. Not the vendor, not us. You are the experts. We can show you how to get to the model, but your model tells you how your facility operates, and you intuitively know how to do that. Good news is that, as I said, and I keep repeating this, everybody is very afraid of statistics, but looking at it this way, it's very simple. You can, instead of those 12 months, you can have 4,800 hours worth of data. It will be still the same model, still same analysis, still same results. And if you need help for that, we would be more than happy to help you with it, with building a model. We cost nothing, and we come from the point of view that we're here to help you. We have nothing to sell. We don't sell piece of equipment. We don't sell meters. We don't sell models. We're there purely to help you understand if the model works for you or how to build it in the first place if you need that. So now that we have our baseline model, if you go on the second tab, you will have slightly rearranged columns. First column will be the timestamp. The second column will be the, I believe, the natural gas consumed, and then the outdoor weather and the production. That is to say, if you're doing this in Excel, any sort of regression model, you have to have all your X variables. And for us, to remind you, X variables are outdoor weather and production output. You have to have them next to each other, otherwise Excel will not work the regression properly. So that's why we rearranged it on the second tab. We put the Y variable, NG consumed, as a first column, and then we put other columns next to it. So out of that piece of information, we'll build a model that's going to give us predicted energy use. In Excel, for those who haven't done this before, if you click on the data field and then data analysis, I hope everybody has that. If not, ask your ESC for help. But if you have that, it'll pop up with something like this. And for those who perhaps don't have this data analysis pack, let us know, and one of the ESCs will come with a laptop and work with you on that. So if majority has come to this point where we have regression, and if we hit regression and we say OK, another pop-up will come up the window like this. So in this window, hopefully you all made it to this window. Is that yes? OK. Input Y range. If you click on this little table on the side of that Y range, you can pick the column that says NG consumed, including the label on the top. You can just pick the whole column. So now we're going to do the same for the X range. We're going to click that little table in the X range. It's going to pop up. And then we pick 2 columns for indoor weather and production all at once, including the labels all the way down in that other table. Because for those of you who have chosen the labels, NG, production, all those, click on the labels field there, checkbox, to include the labels so the Excel will know that the first row is actual labels and will not include it into calculation. If you have not chosen those labels, leave it unchecked. And once you have all that set up, you click on the output range. Where do you want a result to reside? You can do it either on the output range, or you can just say new worksheet ply. And that will open another tab. And the easiest way to do it is the default to say new worksheet ply. Once you click that, you just say OK. So hopefully, this created a new tab in your spreadsheet that looks something like this. It should be same as the tab that you already have there that says results. But the point of this exercise is to show you how the simplest of tools that you already have can generate a regression model for you. You don't need anything more complex than the Excel spreadsheet to start building your model. Once you got this output of the regression, how do you read it? What does it actually mean? For us, for the time being, the most important part is this down here, that area where there are coefficients for intercept, outdoor weather, and production output. So let's see what that does. So if you really look at those 3 factors, it will read something like this. Intercept will be 18,040.938. Outdoor weather will be minus 2,000, and production will be 11. How do they fit into the formula? So as we said, the A is the intercept. So value for the intercept in this case ended up being 18,040 and a little bit. That translates into the first part of our formula. So our predicted natural gas consumption will be 18,040. So no matter what we do in this particular case, we will use 18,040 cubic meters of natural gas. The second one, B1, the slope for the outdoor weather in this case, because that's our second variable, is minus 2,045. That means that the temperature gets multiplied by minus 2,045 in this case, which is fine. The higher the temperature, the less natural gas we're going to use. So that makes sense. If that was for some reason positive, we would have to question why is that the case. There may be a reason, there may not be a reason. But then we would have to question it. Being negative, yeah, that makes kind of sense. And the third one is production output. So if you look at the coefficient for production output, it ended up being 11. And it goes into the formula for production. Volume of production gets multiplied by 11 to go into explanation of our natural gas. That formula is already shown on your second tab where you picked all the things from. On the right-hand side of that tab, there's that formula. It's already pre-populated. So you already have it in place. And what that formula then does, you use it to predict for each month, putting that piece of information in, and then changing the temperature from the outdoor weather for the January, for February, for all of those. Same with the production level for each month. You get what is your predicted natural gas usage. And you will see that your predicted natural gas usage varies a little bit from your actual. It would be extremely strange if they're exactly identical. Good job, but that usually doesn't happen. So you want to be close. That is it. You built energy model. It's as simple as that. And if you have 5 variables rather than just outdoor weather and production output, if you have production output for, yes?
Your outdoor weather,
Yes.
is that the average, minimum, maximum?
No, that's average for that month.
Oh, that's the average.
Yes, average for that month.
How did you calculate the NG predicted?
NG predicted is, see the formula on the top?
Yeah.
18,040 plus in the first line minus 2.1 outdoor weather times minus 2,045 plus production of 21,000 times 11. And then you go line by line. You insert into the, where it says temperature and production, you insert the values from here and here, here and here, here and here to get this number. So if you actually look at the spreadsheet you're given, and if you highlight this field, any one of them, it'll tell you what the formula is. Did that make sense to everybody? So now the next question that you have to ask once you build a model, because it's fairly simple to build, right? I don't think there was that much difficulty in building this model. Is this a correct model? How do we know we build a model that's correct? How do we know it's representative of real life? So now we need a way of assessing the model for the real life data. And this is a very important step. Building a baseline model is very easy. Confirming that it's actually reflective of your production and your conditions is difficult bit. But without that one, you cannot go forward because you will end up in deep problems later on. When is it really important to check the baseline model? More important than other times is when the baseline period is long. Like for example, here we had to wait for a 1 year worth of data to actually build a baseline model. So if your model is wrong, you will have to wait for another year to build another model. So now you're 2 years into implementation, you still don't have a model, much less energy management system in place. So it's really crucial to have this data. When we keep fewer production-related parameters, if all you keep from your production parameters is how many pieces of widgets went through the facility in any given time and nothing else in the historian, then it's really important to build the correct baseline model and check it as quickly as possible because you will not be able to go back and figure out what else drives the energy consumption if need be. So in this case, in our example, in the spreadsheet that we have 2 years worth of data, 24 months. So we used 12 months just now in 2013 to build our model, and we're going to use the other 12 months of already known data to check the model. And if you can do it that way, that's the best way of doing it because now you don't have to wait for another year worth of data. That works well. So simple checks. How do we know the model works well? Check number one that I do, and I had that discussion with one of my ESCs the other day, is what our residuals look like. For those who don't know, residuals are the difference between what we actually consumed minus what model predicted ends up in residuals. For each one of these lines, you do that exercise, NG consumed minus NG predicted is residual. Essentially, what's the difference between what we're predicting and what we actually consumed? And we plot it out. And what we really want to tight and uniform a number around this zero line. Because if it's not tight and uniform, if you have all of your residuals on one side of the zero or on the other, it means that your model is either overestimating and underestimating for some reason. So you really ideally want to have the same number of dots or within 1 or 2 dots above and below the line, and you want them in the same rough area. So you don't want this one dot to be over here all by itself and everything else here. That tells you there's something off with the model. We don't know what it is, but something is off. So that's number one way to check your model. If residuals don't look good, model probably can use some more work. What are the values associated with key model parameters? Now we're going back into what everybody focuses on when they first create regression model. They get all excited about R-squared and correlation. Adjusted R-squared, standard error, F-statistics, p-value, and constant. Those are the things you should be checking for if you want to know if your model is correct. So where do we find those? In green, it's highlighted R squared, adjusted R squared, standard error, where F is on that line, and then p-value for all three intercepts. And these are just pulled out of that table for you to see it better. So what is adjusted R2? Does anybody know what the difference is between adjusted R2 and R squared and regular R squared or multiple R squared? If you look at the picture here, you will have on the left-hand side, you will have multiple R's, 0.978, R squared, 0.958, adjusted R squared, 0.948. Right? If you have more than one parameter, and in this case we had two, we had outdoor weather and we had production in the X variables, you really need to look at adjusted R squared and only at adjusted R squared of all of them. Because that will tell you two things. R squared in general tells you how much of the predicted variable, whatever it is, in our case natural gas, is to be explained by the variables that we put into X field. So production and outdoor weather. In our case, it was about 95% of all the predicted value of natural gas is explained by either outdoor weather or production, or combination of both. Multiple R squared will increase your value. If you have 15 parameters explaining your natural gas consumption, your multiple R squared will be very close to 1. The more parameters you put in, the closer to 1 you get, which sounds good. Except you can put any sort of garbage data into these values, increase R squared, multiple R squared, without increasing the accuracy of your model, if that makes sense. So the more of these lines here you have, the better multiple R squared will get. And if you see it there, it's 0.978. It's the best of all R squares listed. And if I put here distance to the moon and circumference of the Earth, it would get even better. But it wouldn't explain your natural gas usage. So every time you have to put more parameters, multiple R will get bigger and better, but it's meaningless. So really what you want to focus on is adjusted R squared. And adjusted R squared in our case is 0.949. So 95% of all the predicted natural gas usage can be attributed to outdoor weather and or production. So that's number one. Number two, standard error. If you remember the standard error in the image. High standard error is indication that model is not as reliable as it could be. So for example, in this case, standard error was 4,857 out of the constant of 18,000. So almost close to 1/3 of our intercept was actually an error. So we could be 18,000 plus minus 4,800, which is not very good. Sometimes it is what it is, but you have to keep that in mind. F statistics. From the statistics itself, it determines that if that independent variable taken as a whole explains the dependent variable. So F statistics, if you look at the model and your F statistics is 10 or nowhere close to something on a minus, on the power of -5 or -6, your model is statistically not really valid to begin with. You essentially guessed at it, and the model is guessing at it as well. So you want that F statistics to be very, very low. The lower, the better. I forgot where we were on that. F statistics in this case, 102, significance was on -0.07. So you want this one to be very low based on this one. So that's a very good number. p-value. It's a confidence level. P-value for all of those three, it tells you probability of being wrong when concluding there is a statistical significance, which it tells you essentially if this p-value here is high, it tells you that it's probably wrong to begin with, and it shouldn't be included in the model. So usually what I do is I usually put as many parameters as I can find in the production process to explain the consumption, run the first regression, and see how many of them come out to be bigger than 0.05. Because you remember we put in our model, we put 95% accuracy. So p-value should always be less than 0.05, except for the intercept. Intercept is different. Intercept has its own rules. But any x variable should have p-value less than 0.05. If it doesn't, if it's higher than that, remove it from your model and rerun it again. Because you will find that that other parameter then gets more accurate than it originally was, and your whole model will improve a little bit. And the intercept as well. For me, when I look at the data, and if I have very high intercept that I cannot explain, tells me something's wrong with the model to begin with. If I can explain it, if I can say, you know, I'm running this oven, and the oven constantly uses gas, and no matter what I do with the production, my oven will constantly use gas, there is a reason for that high intercept. That's perfectly fine. But you have to understand it. You have to intuitively be able to explain to yourself, does that make sense? Do I really use 100,000 cubic meters of gas every month, regardless whether I make widgets or not? So in this case, model was pretty good as it is. Most people would accept it as is. And from now on, they would raise their hand and they would say, I have an energy model. They would go in front of the management and they would say, I can now predict my energy use going forward, no matter what. And that's a very exciting statement, and it's a very dangerous statement. Because from now on in, if you're working in corporate settings, your facility might be measured against other facilities in the world based on your model, because you said it's accurate. You said it predicts it well. So we will see how accurate it is based on comparison with other sites. The more important thing immediately is that the budget might be proportioned based on that model. If I go to the management and say, my model can predict that if we cut back 20% of my production next year, I can use 38% less natural gas, management tends to go, OK, your budget is less 38% next year. Now, if your model is not as correct as you think it is, you will run negative budget, which is really bad in corporate world. As far as I can remember on my side. So we want to be sure that we use the proper model in a proper setting before we raise our hand and we tell the management, go ahead, judge us against that model. So how do we do this? In our case, we have 24 months worth of data, we said. We have 2013 and 2014 in that spreadsheet. So we'll use 2013 model to model 2014 before we tell everybody how smart we are. Because we want to see what known information is going to tell us about our model. So this was our model. So we will use the same formula, because remember, now you built a model that accounts for temperature and accounts for production, so you can predict the future. You can put this, even though we built it for 2013, you can put this into 2014 data. You can then 2014 data for temperature for each month and production for each month, and you can get predicted value of natural gas for that month in 2014. So that's just a straight exercise putting the information in, and you will have in your spreadsheet on the, I believe, third tab, you will have what is the predicted usage for that month in 2014 using 2013 formula. Now, if you do that, so now it changes. We go from natural gas that's consumed, we look at natural gas that we predict ourselves. What is the prediction? What do we expect in 2014 based on 2013 run? And then we get to energy consumed. We already know that because that's in the past. We had the data. So now we know what we actually consumed and how does it compare to the predicted model. And in this particular case, we actually use more energy than we predicted. So if this is a small percentage, of course, this is just an example, but I've seen these percentages going in 10, 20% over based on the models. So if you were to offer that baseline model already to your management, you would be off by this much. So there's something wrong with the model. Yes?
How are you going to predict that if you have no prediction of what the weather's going to be in the winter, how long winter's going to last?
In this case, we have it because it's 1 year behind, right? But there's always, a lot of companies will buy natural gas based on the expected weather. So they know what the expected weather is based on 30-year average, right? So when we do, for example, when we work with you and where we use calculation of any sort of seasonality in our information.
How accurate is that even? Like,
It's,
when I looked at the temperature for September 2 months ago, it was not showing these hot days.
yeah, for sure. There's variability, of course. And there could be climate change. There could be all sorts of reasons that the data is not accurate. But you have no other way of predicting it, right?
That will be, like, you will be able to justify if that month is higher.
Because it was colder.
Because now you can tell that you have a different weather than the predicted.
Yeah.
So one of the things that will happen, and that's a very good point, is you will build this model. Let's say you didn't have this data. You're guessing at the numbers based on averages. You build the model and you say to management, this is what I expect. And you really end up with this afterwards. But then you go, oh, but this was not 16.7. It was 21 degrees. Or it was 10 degrees. You will have explanation, and then your model will change this. But if your model is wrong, no matter what you put in it, it will not improve on it. So that's the point of prediction, to say, hey, does that make sense or not? Because you want to predict forward, but then you want to have a rational explanation why the prediction was not correct. And change in temperature, change in climate is a rational explanation. A wrong model is not a rational explanation. So what happened? And what happens in more cases that I care to remember is that if we look at the logbook, we have to keep, when we do energy management, one of the things that I want people to do is keep a logbook of their actions. Every time they change something, make a note, date and what changed. So that when your model works, you can say, oh, but I changed something on this date, my model shows a little bit change. Okay, I understand where that change comes from. If you don't have logbook, you work with like, I have no idea what happened 6 months ago. I cannot explain whether that's right or wrong. If we strongly feel that the results should have been different, and we have not tested the model before, so this is not a model that we used for 10 years, it was proven to be correct, and now we claim that it's not correct, well, then it's time maybe to look at what our energy drivers really are. Because that's the only way that the model can be wrong. Bearing some typo or something like that, energy driver is, unidentified energy driver is the reason why the model is wrong. So we said we went to the production people and we asked them about all their inputs. And the question that we have to ask ourselves, did we really find all the reasons? And in this case, I used the relatively obscure reason why this can happen. And most of you will laugh and say this is not possible, and I can tell you that it is possible because it happened to us. We had a steel processing facility, and our material was stored outdoors, and we never accounted for the fact that it's sometimes in the snow and sometimes it's not. And what happens to the snow and the moisture when you put it into the oven, it tends to use a lot of energy to evaporate first, which changes your energy. So point of the story is that you have to identify all of the energy drivers, all of them. No matter how insignificant they seem to start with, put them all in some sort of priority level, because you don't know which one you're going to use. So in this case, as I said, material stored outdoors, it's covered, it's exposed to snow drifts. So now we have to go back and we say, oh, snow accumulation for 2013 is going to be another parameter for our facility. Now, in our case, snow accumulation is something that's available in the historical records of the Canadian National Climate Site. But if this parameter was something to do with the production that we didn't track, remember how we talked about posted notes and what is happening with the production? If we didn't track that, there's no way for us to go back and check it. So now we have to track it for a year forward. And we cannot use the model. We actually have to build the model for 1 year forward. We wasted all that time for nothing if we didn't track that. So now we have 3 independent variables. Formula is the same. And this is one of the key points that I want you to take, that the formula is always the same. We just keep adding pluses at the end. Whatever the energy driver is times another slope factor. You can go to 50 if you need. So complexity is no different. It's exactly the same. You would do exactly the same thing. We will not go through it. You have in this spreadsheet that we gave you as an example, you have an example there. There is no need to go through it because the mechanics of it are exactly the same. You pick the y variable, you pick all the x variables, you build a model. That model will give you a regression results, regardless how many of these you have. So in this case, we'll get a formula that says this. Notice that now production has slightly changed, temperature has changed, and our intercept has dropped off. So these are the new values. So now if we go back into 2014, because we have the data for 2014, and remember how we tested our baseline model from 2013 with 2014 data? We can do the same with added parameter. So now we have 3 parameters, including the snow accumulation for 2014, which is different than it was in 2013. And we have new predicted values for the natural gas usage. We compare that to the consumed. This time around, we actually have savings. Last time, we spent almost 2% more energy than we thought we would. Now we're spending almost 1% less than we thought we would. Again, don't be alarmed by the actual absolute values. It's the direction that's important to you. If your model is telling you savings versus overspent, that's important. That's what you want to get to before you're on the hook for the results of the model. So now people will say, oh, what's the big deal? We already said you changed your facility from energy overconsumer to energy saver. But the more important thing is lots of people will be saying, oh, but the percentages are so small. How do I know which one is correct? How do you know the other one wasn't correct and this one is really wrong? And one thing, remember that other one about statistics and lies? There's another one that says that essentially all models are wrong. Some of them are more useful than the others. So you have to keep that in mind. These George Box and the Israeli are all very important statistics people. So these are not people who shun statistics. These are people who are very good at statistics. And yet, that's what they're telling us. So keep in mind, common sense overrides the model. So let's compare now 2 models that we got. On the right-hand side, you will have the old model with 2 parameters. On the left-hand side is the new model with 3 parameters. So let's see. Adjusted R-squared because we said we don't look at R-squared by itself, because you see how R-squared increased. This one went down a little bit. So our correlation actually lost a little bit of the ground. But our standard error is almost 25% less. Our intercept is now only about 14,500 versus 18,000 cubic meters, which means we are closer now to explaining more of the natural gas usage than we were before. It's not drastic changes. They're small changes, but they're in the right direction. So these are all the changes. Intercept got smaller. Standard error improved. In other words, we want to get to the point where we're comfortable with the model. The model tells us this is where you should be. We checked it against the next year. It seems to be better. So now we go ahead, we use this model for the future. So don't look at just absolute numbers. Look at values. Look at how much it moved by. Did it move in the right direction? Did it move in the wrong direction? That's what's really important to find out. So when you do your own model, start with as many parameters as you can identify. Even those that seem very useless and you would think they don't affect energy, put it into the model because it's really easy to create a model. And you will quickly know whether you're correct in your assessment that it's not useful parameter or not. Just remove it when you run next time around. It's much easier to remove than it is to add. Check those key parameters. Do they make sense? If they make sense, go ahead. We said those drivers that are not influential, if we had any, they will be identified by the p-values higher than 0.05. If we have those, remove those in the next run of regression model. So if you have to start with 5 parameters that you identified as important and you go down to 3, that's OK. At least you will be satisfied that you didn't miss anything. And keep iterating that until you're satisfied with the model that you got the best numbers you can. As you've seen today, even for those who did this for the first time, it was very easy to actually generate a regression model. That took, what, 5, 10 minutes worth of work. Once you're familiar with the steps, it'll take you a minute to generate a regression model if you have the data. So it's better to spend 5 minutes generating 5 models, getting to the one that you like, rather than spending no time and spending 1 minute and say, I'm done, getting it over with, and then be on the hook for the wrong model later on. And do a reality check. Does consumption drop with the outdoor temperature rise? If it doesn't, do we have an explanation why is that the case or not? If we don't have explanation, time to go back and redo the model. Model is not magic. It will not do anything that we as thinking engineers cannot do ourselves. So if we cannot come up with the same direction of conclusion, there's probably something wrong with the model. So this is really, to me, important part. Without the calibrated is key. We use 2014 here to calibrate our baseline. Without calibrated baseline, your energy model is house of cards. It will fall down. It's not a matter of whether if or not. It will fall down. It's a matter of when. So you can go ahead for longer. You may even get to another position and not worry about energy model anymore, but that energy model will fail. Baseline also is your map, like a treasure map. It will tell you where to look for opportunities. It will help you identify opportunities. It will help you justify opportunities. It will help you with accountants to tell them, look, I know exactly how much I can save. Here's the model. And they will trust that far more than we will. And use that baseline to teach others in the organization on the benefits. Why is it important to change the setting? Because now if one of your parameters, for example, is the setting on oven, whether it's 400 degrees F or 395 degrees F, the model will actually then predict what is the consumption with the lower setting. So when you go to the production person and say, I want you to change this by 10 degrees F, you can actually give them a value for that. So you can tell them, you're contributing to this organization for so much savings with the number attached to it, rather than saying, just do it because they said so. And when you get somebody's engagement, you will get far more out of that operator than you would just by issuing edicts that they have to do better. It's no different than continuous improvement in your facilities. Energy management can be viewed as one branch of continuous improvement. It doesn't have to be a separate stream of business processes. Actually, the closer it is to continuous improvement, the better it is, because people understand it, and everybody will buy into it. It's not a separate offshoot here on the side. It's part of the continuous improvement efforts. Kaizen had a thing that's called document reality. So when you go and do something, you go around and you document what is it that you actually situation is today. That's the same thing as building baseline for energy management model. It's exactly the same thing. What is it that we're doing today? How does that affect the outcome? What the outcome is. So properly calibrated baseline. I mean, how many times can you say that you can predict the future? Properly calibrated baseline will allow you to predict the future. It will help you identify potential savings and investments. Again, if you know that a baseline is correct, you can play with the inputs. If one of the inputs is production on line number 3 versus production on line number 1, you can say which line is better to run if you have that flexibility. Maybe I can run more on line number 1 than on line number 3, and I can justify that in terms of dollars and cents, not in better, worse. You can actually justify that in dollars and cents. And if you have customers that require you to be more efficient every year in energy efficiency because they want to be seen as green in their store shelves, this kind of record is verifiable. You can always show it to your customers. You can say, look, we're saving this much. Here's the model. That will avoid all sorts of auditors from their part coming into your facility judging you. The other thing is some of the important parts is verify the savings from equipment upgrades. Very often we get into a situation where vendors come in, promise you 30% savings, 20% savings, this or that. I have not yet seen anybody who guarantees energy savings when they sell you something like that. Personally, I would always ask, if somebody throws that number at me, I would ask that in a written form. And usual answer will be, oh, we can't give you that because we can't predict what's going to happen. Well, you have a model. How about we use the model? If model shows that I didn't save as much, I claw back 25%. And let's see how many of those promises will stick. Right? So you can do a lot of things with the proper model. Once you're confident of the model, you can do a lot of things with it. So in summary, what are the steps to set up the energy model? When you really think about it, you define the boundary base year. You observe energy use. And observing is not metering necessarily. Identifying, analyzing, and then metering. You prioritize energy drivers. What are the important ones? What are less important ones? You build that baseline model. You verify it if you have the data for verification. That's very important. If not, I would say keep the model to yourself for a first little while until you can test it with more historical data. And then use it in all those things that we mentioned already. So those steps, if you really look at it, that's how you're going to manage it. That's how you're going to manage the model once it's in place. You will observe what your energy use is. You will identify improvements. You will execute those improvements, whether that's capital investment, whether that's maintenance, whatever it is. You will verify the impact through the model, and then you're going to act. You're going to say, oh, I changed the operational parameters on this line. I verified the impact after X months. Now that's going to be a standard practice. So you don't have night shift, day shift problem, where day shift is somehow 30% better in the energy use than night shift, and you have no idea why. You can use this, and then you can tell there's no variability. We know it works. We know what the impact is. Use those settings. And for all of you in the industrial setting, this is no different than your continuous improvement. I mean, replace the words in it, but it's essentially the same thing. So when you talk energy management to your managers, you can talk in continuous improvement ways. It's exactly the same thing. And the results are the same, by the way. If you properly execute the changes and verify the impact, introduce new operating standards on new equipment, you will get the savings just like you would get savings with the continuous improvement drive for better scrap rates or whatever it is else that you're doing. It's exactly the same. And action. This is important to stress. Action is the element of energy management success. It's a keystone element. Without action, nothing will happen. We can talk about it here. You can go into your offices. We can say, yeah, we have energy management plan in place. If somebody doesn't do something, everything falls apart. You can have all of these things. You can have data collection. You can have meters. I've seen meters, almost $1 million worth of investment, sitting unused. You can have information interpretation, so understanding. You can even have understanding which action needs to be taken. You can report it. You can have notifications sent to the operator. Change it now. And that needs to happen. Somebody needs to take corrective action. If that doesn't happen, everything else falls apart. So if the guy doesn't or girl doesn't want to do anything, all the rest is gone. You might as well not bother. So my energy management drive would always start from the production people and say, if I give you information, will you change something in the way you approach your production? And if they don't do that, I guarantee you're wasting your time. You will be looking good. You can even claim you have processes in place, but you will never actually realize the savings. So you have to start with the production. Are they flexible enough? And building the baseline model, if nothing else, if your R-square shows, for example, when you do it and you include all your drivers, and it says 60%, if your R-square is 0.6, it tells you that 40% of the energy is inexplainable to you. 40% of that energy facility has no idea where it goes. And then you put 40% of whatever your usage is, and you say, is this amount of money, let's say $50,000 a year, is this enough to make you change how you run your process? But then you have the number in place. So baseline is always valuable to do, whether you actually go into the management system or not. Baseline is a very powerful thing. Again, for our program, we can help you with breaking down that complexity, and we provide additional funding. We can connect you with appropriate contacts at other utilities if you need that. And these are the financial incentives that we have. 80% up to maximum $40,000 per initiative for implementation of EMIS infrastructure, so meters, calibration of your meters, whatever else you have, that will help you get the data where it needs to be. 50% up to maximum $100,000 for implementation of projects. So if we do baseline, you implement the system, and then you identify capital project, then you fall into our typical custom program, where we give you money up to $100,000 towards the capital improvement. And you can discuss those fine details with your energy solution consultant in charge. So that's all I had. Is there any questions or comments or any concerns? Excellent. So everybody was clear. Good. I'll see you in a month with your baseline models. Thank you very much for coming. Thank you for your time.
Thank you.